Here we go. So the reason why I stuck with little a and little b, looking at rectangular form of polar coordinates, was that that will be exactly the same for looking at complex numbers. So first, in rectangular form, we have the real axis and the imaginary axis. So that a point, say, and usually complex numbers use the letter z rather than x or y. So if z is equal to 2 minus 3i, we would go 2 on the real axis and 3 down on the imaginary. So z1 is right there. Where would we plot the number -4? In other words, what if we don't have an imaginary part?
Wouldn't it just be on the x-axis?
Perfect. Yes.
Real one, sorry.
Yeah, exactly right. And what if we have a number that is purely imaginary?
And it would just be on the imaginary axis.
Good. One thing that I think is important is that I've seen often people saying that uh, I is defined to be the square root of -1. And this is a true fact, but this is not the definition. The definition comes from I squared. I is the only number you can square and get a negative answer. So this is its raison d'etre. This is what gave birth to I. And then everything went from there. It's just amazing to me that actual real things in the world have equations describing them with complex numbers. So they're not real, they're just different. You can see with this little sketch that we can define a point z using a plus bi or using r comma theta. And we're going to go back and forth in exactly the same way that we did with purely polar form. We've got some notation. The modulus of a complex number is like its magnitude or its length. The notation looks like absolute value, but this is R. This is defined to be the square root of a squared plus b squared. So if you see something that looks like absolute value, but you're in polar form, you want to, you're looking at a two-dimensional thing. Then you take the square of the numbers, add them, and take the square root. So let's find Let's find the modulus of these 4 points. For Z1, we've got little a is 3, little b is -3. So we have 9 plus 9 is 18. 18 is 2 times 9. We can bring that square root of 9 out, and that's 3 times the square root of 2. So R, or the modulus of this particular complex number, is 3 square root of 2. The angle, well, let's see. The tangent of the angle will be little b over little a. Little b is -3. Little a is 2. So we get, oh no, little a is 3. Yay. So we get -1. The only angle that has a tangent of -1 is -pi/4 if it's invertible. And let's see if that's the right place. Z1 is in quadrant 4, so this is great. If we had noticed that Z1 was in quadrant 2, we would have done 180 or pi minus pi/4. Okay. Oh, notation. So when you have a polar, a complex number in polar form, you can express it as z r comma theta, but more often you'll see z equals r times cosine theta plus I sine theta. And these thetas are the same. So like, for instance, this point that we just messed with would be, we said that r was 3 square root of 2. That theta was -pi/4. And we would leave it like that. So when I was going through school, I wanted to evaluate this. But if you evaluate it, you'll end up back with rectangular coordinates, a plus bi. So you don't want to evaluate this. You want to leave it. The notation that is better is Euler's form, which is that r cosine theta plus I sine theta is r times e to the I theta. And this notation is what you'll use most of the time if you take engineering or physics classes. Oh, it looks like Sunday morning, this coming Sunday morning, we're not going to have we're not going to have ACES or Canvas or anything until noon. All right, so we've got these 3 forms. To find r, we're going to take a squared plus b squared square root And to find theta, theta is called the argument. And we know that the tangent of theta is b over a. So let's find here we go. Let's find the argument. We already did 3 minus 3i. Let's find the argument of, although these two are pretty easy. This one is -1, which means negative, where it'll just be pi. And this is going to be 4i, so it's at the top, so it'll be pi over 2. And let's do this one. So we've got v4 is -2 plus 4i. That means that little a is -2, little b is 4. That means we're in quadrant 3, quadrant 2. So we're in quadrant 2, and the tangent that we get automatically is going to be in quadrant 4. So we'll have to move it. So it really is important to locate the quadrant your point is in. All right, so we've got r is a squared plus b squared square root. A squared is 4, b squared is 16. Square root of 20, we can write this as 4 times 5, and the square root of 4 is 2. For the argument, we have theta is equal to the arctan, or the inverse tan, of b over a b is 4, a is -2. 4 divided by -2 is just -2. Oh my, sorry, my calculator fell under the table. Just a second. All right. So if we have -2, and I'm finding the inverse tangent, I get -63.4. Excuse me. This is in quadrant 4. So if I add 180 to that, I get 116.6. That'll be the angle in quadrant 2. So it'll be, let's see, 116. This is 120. This is 90. So 116 is going to be over here somewhere. And it should be directly opposite this 60. -63. So let's see. Yeah, it looks good. And we said that r was 2 square root of 5. Let's see. 5 square root times 2 is 4.5. Go 1, 2, 3, 4.5. and this is the point. We can write it as r theta. So 2 square root of 5, 1/16, I think it was. Or we could write it as r cosine theta sine theta. So 2 square root of 5 cosine of, and now we need in this form, excuse me, in this form, we need the angle to be in radians. So I'm gonna do this. Oh, come on, go away. Pardon me. Here we go. So we've got -2, and I'm going to do inverse tan in radians. And I'd like to know how many pi's are in this. So I'm going to divide by pi. So the angle is -0.4 pi plus I sine -0.4 pi. Did you see how I did that? I made sure I was in radians. The value I got included pi, so I divided by pi so that I could write the angle as a multiple of pi. Okay. The next thing we're going to do is multiply and divide, because why not? If we have two complex numbers in rectangular form, to multiply them, it's just exactly what you would expect. We're going to distribute. And we're going to remember that I squared is -1. So the powers of I is a really wonderful thing. We have I squared is -1, I cubed, that's I times -1, so that's just -I. I to the 4th is, wait, that's I squared times I squared. So -1 times -1 is +1. I to the 5th is I times I to the 4th. So it's just I times 1, which is just I. So you can see that powers of I are cyclic. We have I, -1, -I, 1, I, -1, -I, 1, I. All right, so let's find the product of Z1 and Z2 if Z1 is 3 plus 4I and Z2 is 2 minus 2 square root of 2I. So we're just going to distribute. We've got 3 plus 4I, 2 minus 2 square root of 2I. 3 times 2 is 6. 3 times -2 square root of 2I is -6 square root of 2I. And then we have 8I. And then minus 8 square root of 2i squared. So minus 8 square root of 2i squared. But I squared is -1. This is weird. So let's see, -1 times a -8 is a +8. And I'm going to move this down front because this is now real. So we have 6 plus 8 square root of 2 minus, and let's just write these two I terms together. 6 square root of 2 minus 8i. And I have a minus here in front of the 8 because I put a negative in the front of these parentheses. So it's possible to find the product. It's not beautiful, but that's okay. But check this out. Let's let Z be R1 cosine theta 1 plus I sine theta 1. And let's let Z2 be R2 cosine theta 2 plus I sine theta 2 to multiply we multiply the r's, so R1 times R2, and we add the arguments. We add theta 1 and theta 2. So we have cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And that's kind of gorgeous. And in our next class, Wednesday's class, we'll see the first beautiful discovery that builds on this. So let's take two complex numbers that are in polar form and find their product. I think I must have missed a page. I somehow missed page 2. Just one moment, por favor.